This is part 2 of the Earth Resources topic on AQA GCSE chemistry. It's a dual award topic, which means triple award students will need to learn it as well. This particular chapter, the Earth Resources, is quite fragmented, so this doesn't really follow on from what came before. In this video, we are going to look at how water is made safe to drink. And I'm going to recommend you pause and try the activities before you review, as always. So we need to know the difference between pure and potable water. We need to explain how groundwater is treated so that it's fit to drink, and we're also going to compare that to how we might prepare salt water to drink as well. And that's going to tie into a practical that we're going to review. So why do we need water? Well, there are some very obvious answers, but let's go through a few of them. We need it as a solvent in many different chemical reactions, as a coolant in industry, we need it for washing and cleaning, we need it for cooking, and obviously we need it for drinking. It's fairly central to everything that we do. But the water that's in reservoirs is not fit to drink, and there is a process that looks quite complicated. I'm going to run through it very, very quickly, and then see if I can summarise it a little. But it might be worth you taking a read through and double checking what your understanding is before listening to me. So if we take the water in the reservoir, the first thing we do is pass it through screens. These are relatively open, and that's to get rid of large objects. So we're still going to get small bits of debris going through, but we're getting rid of the bigger bits. Once we've done that, we move through to a settlement tank. Any solids that have got through are allowed to sediment at the bottom, and then we can almost decant the liquid around. So we're leaving a lot of the solid behind. Now, when we pass it around, we've still got small amounts of solid impurity that are coming through. They have managed to stay dispersed in the water, so what we do is add aluminium sulfate and lime, and that causes those small pieces to clump together so that they will then settle in the next tank. The water can then carry on. We've still not got rid of all of the solid waste yet, but it comes through and it's filtered through very fine sand. So that will get rid of the vast majority of the solid waste, however tiny those particles might be. Now at that point, we've got water that might look clean, but it isn't, because we've not done anything to get rid of bacteria. So at this point, we treat it with chlorine that kills the bacteria, and the water is then ready to come to homes, to offices, to schools, and to factories, ready for us to drink. So is the water we've got at the end of this pure? And the answer to that is no. We've got rid of bits of solid waste, we've got rid of bacteria, but what we have not done is got rid of the salts that are dissolved in there, for example. And we spoke in a previous chapter about purity in chemistry. It means made of only one type of substance. What we have got is potable water. We need the definition for that term potable. And when we say potable, we mean water that is fit to drink. So a practical that goes alongside this, what if we were actually trying to separate out water from salt water? If we had seawater, if we were an island surrounded by sea with no fresh water supplies, we would need to not just go through the process that we did there. And this practical takes you through. There's a lot of information here. I'm going to talk it through, but I'm going to show you the diagram as well. So we take tap water and crushed ice to make an ice bath. We take a boiling tube, we put that in the ice bath. You'll see this in a second. That's what we're collecting our pure water in. We're going to add the solution we're distilling, which is salt water in this case, into a boiling tube with a 2-hole bung with a thermometer going through again. We're then going to heat it. This is a standard distillation practical that you will hopefully be familiar with. We're going to ignite the Bunsen, air hole closed, open the air hole to get a roaring flame. We're going to note the temperature so that we can see at what temperature it starts to boil, and we're going to collect the water. So this is the sample that we're testing. In our case, it's salt water. We have got the delivery tube going through to pure water, collecting the pure water in the boiling tube. The boiling tube is in ice, and that's so we can try to condense some of the water vapour as it comes down the delivery tube. And the route that it takes as we heat it, the water evaporates, it becomes steam or water vapour, it moves around, it cools, surrounded by ice, and it drips down as pure water. So, let's have a think about some questions. Now, we did this with salt water to purify it to make drinkable water. What if we'd done ethanol? Why might we not use a Bunsen burner? And it's a straightforward answer. Ethanol is flammable. Having a naked flame directly below it would be very, very dangerous. It could ignite. It could cause an explosion. What was the boiling point and the pH of the solution that we tested? So bear in mind we did salt water, we were collecting pure water. Let's go with what we would expect it to be if it were pure. And it's 100 degrees Celsius, and the pH we would expect to be 7. Predict the yield if a condenser had been used. You're used to doing this with a Liebig condenser with a jacket of cold water. We would expect the yield to be higher. Even with the ice in the beaker, some of the water vapour is going to escape into the atmosphere before it condenses in this particular apparatus. Calculate the percentage difference of your boiling point compared to the actual value. Well, we've not done the practical, so we can't do it, but let's have a look at what we would do. We know pure water would have a boiling point of 100 degrees C. So that's the temperature we would read on the thermometer at the point the water vapour is passing it. The further away from 100 degrees C, the more impurities would be present. And so we could look and say, if it's 101 degrees Celsius, we could be quite confident. If it was 115 degrees Celsius or 75 degrees Celsius, we might be less confident in our results. That takes us to the end of this video. Thank you for listening, and goodbye.